So, good evening, everyone. Welcome to the ninth live session for the course Concrete Technology offered by NPTEL. I am Harshit Agrawal, a PMRF scholar from the Department of Civil Engineering, and I will be taking weekly live session for the entire course duration. So, in today's session, we'll first have a quick recap to the week 8 live session discussion that we had last week, and then we'll look into the things that are covered in the week 9 content of the course. Okay, so the week 9 content that we'll discuss today it will be in continuation of our discussion on mechanical properties of concrete. So, for this session, we will have following discussions. It will be first we'll start with elastic modulus of concrete, then we'll see fatigue in concrete, bond strength of concrete, creep in concrete, and shrinkage in concrete. In between, I have some objective and numerical questions for you, around 18 questions in total that will challenge your understanding of the concepts. And finally, we'll conclude the session and I will try to address any other queries post discussion. So last week we concluded the eighth week of the course where we talked about strength of concrete. We discussed why concrete has higher compressive strength than tensile strength, and we saw two theories that support this discussion. One theory is based on cement paste via CSH bonding, and the other was based on crack propagation in concrete. We saw how cracking patterns differ inside and outside concrete. For inside concrete, we saw how cracks and pores they affect the strength of concrete by discussing about Griffith's theory and Power's law. We understood why crack propagates through ITZ. Why? Since ITZ has higher proportion of porosity than bulk cement, it makes it prone to cracking, and that's why we say in a concrete the cracking propagates through ITZ. Then we talked about how cement paste affects the concrete strength through this flow chart. So we discussed how type of cement, age of cement paste, curing condition, and admixtures used. They all affects the degree of hydration and gel structure and composition. W by C ratio and degree of hydration, it affects the porosity, which affects the strength, while gel composition and structure, it affects the densification of concrete, which affects the strength. Then we talked about how aggregates affect the paste bond, aggregate paste bond, and directly the concrete also through this flowchart. So aggregate quality in terms of surface roughness and chemical composition, they can affect the bond between cement paste and aggregate, which can affect the strength. While aggregate proportion, amount of aggregates that are there in concrete, the particle size of aggregates and the modulus of elasticity of aggregate, they all can directly affect the strength of concrete. Then, apart from effect of different concreting element on the compressive strength, we saw how testing setup and sample dimension can also affect the strength of concrete. In this, we saw how specific requirements that are there in IS 516 for compression testing, like sample shape, sample dimension, loading rate, moisture content, and capping material, affects the concrete compressive strength. And finally, we talked about tensile strength of concrete and different ways in which indirect tensile strength of concrete can be determined. That was using split tensile testing and modulus of rupture testing. So, this was all from the previous session that we discussed. I hope there are no doubts in the previous session to anyone. If you have any doubts, you can just post your query in the chat box. In between, when I will stop the session for discussing some questions, I will look at those doubts also and I will try to address them. Okay. So now the next part that we will be discussing will be the elastic modulus of concrete. So what is elastic modulus, or generally we say modulus of elasticity? So simply saying, it is the ratio of applied stress to corresponding strain. Okay, which determines the ability of concrete to withstand deformation due to applied stress. Okay, so now, so if a concrete is stiff, we say it deforms less under a applied stress. Okay, so like when we do compression testing of concrete, we are applying stress on concrete. Okay, so due to this stress, there is strain in concrete, that there is deformation in concrete. So this ratio of stress to the strain in concrete, this is known as elastic modulus of concrete. Okay, now when we apply such compressive load on concrete and we measure both axial stress and axial strain in concrete, it is observed that concrete shows a non-linear inelastic behavior. Okay, so why is that so? So for that, first of all, what this non-linear inelastic behavior means. Okay, so non-linear behavior means that strain is not linearly increasing with stress. So you can see in this profile, it is not linear growth. Linear growth will be like this, but it is deviating from linearity. So this is non-linear behavior. Like, and so initially the rate of strain is low, okay, as the stress is increasing, and slowly the rate of strain is increasing as stress increases. So this is non-linear behavior. And inelastic means that if I have removed the applied stress, then concrete won't regain its original shape again. There will be some strain that will be left in concrete, there will be some deformation that will be there. Okay, so that's why it is said non inelastic. Okay, so that's why we say concrete shows a non-linear inelastic behavior. Okay, now why concrete shows a non-linear inelastic behavior? Because it is because of the way crack propagates in concrete. Okay, so at lower stress level, suppose this is my ultimate load at which failure of concrete occurs. This is ultimate load. So at lower stress level, up till 30%, suppose of up till 30% of this ultimate load, what is happening? There are micro cracks that are forming at the ITZ. Okay, and at this point you can see the straight this curve, it has already started to deviate from the linearity. Okay, this indicates that non-linearity is reached even before peak load. Okay, now if I will remove the load at this point, then what I will see, it will regain its it will again regain some of its strain. Most of the strain will be recovered, but only a small amount of permanent strain will remain. That is due to the micro cracking that has occurred at the ITZ. Okay, that can't be recovered. Okay, now suppose I applied the load very near to the peak load. Okay, so suppose at this point I have reached. Okay, now what has happened till this point? The micro cracks that are there inside the concrete, they have widened up and new cracks are formed. Okay, due to which there is non-linear behavior in concrete. Now there is stress distribution that is occurring around the crack. Okay, so at this point, if I will remove the load, then what will happen? I will see a hysteresis effect. Okay, meaning that some energy is dissipated in the internal damage which can't be recovered, and there will be some permanent strain left in the concrete. Okay, so you can see this also a hysteresis effect that you can see. Okay, this is the permanent strain that is left inside the concrete because some energy is lost in the cracking of concrete which can't be recovered. Okay, now if I apply load beyond this point, okay, so what will happen? Micro cracks, they will combine to form a large crack which will cause softening of concrete. Concrete will lose its load carrying capacity which will lead to brittle failure, and if the load is removed, a large permanent deformation strain will remain, and the unloading curve will be much flatter, indicating stiffness loss. So what will be there? This is the curve, then this will be something like this. Okay, the concrete has failed now. Now if I will remove the strain at this point, you will see that only a small portion or maybe no portion of strain will recover. Okay, there will be a there will be a permanent deformation that will be there inside concrete because concrete has already failed. Okay, so that's why we saw in this that's why we say that before reaching the ultimate load pu, the concrete stores a non-linear inelastic behavior in compression. Okay, now since this behavior is non-linear, uh, there can be multiple ways in which modulus of elasticity of concrete can be estimated. Why? Because of non-linearity, we know modulus of elasticity is nothing but ratio of stress upon strain. So if it would have been a linear behavior, then it would be the slope of the line which will define the modulus of elasticity. But here it is not a linear behavior. Okay, it is a non-linear behavior. So that's why there are multiple ways in which we can define the modulus of elasticity. Okay, which is basically the rate of change of slope. Okay, in a linear behavior, the rate of change of slope is constant, so modulus of elasticity will be constant. But here, there can be different ways in which we can define the modulus of elasticity. Okay, so the first way is known as initial tangent modulus. Okay, so this is like where slope of stress versus strain is determined at the initial point of loading. So at this point, if I'm determining the slope of the line, then it will be my initial tangent modulus. Then instantaneous tangent modulus. So this is like MOE value is estimated at any point by drawing a tangent. So at any point in the stress strain curve, if I draw a tangent, then the slope of that line is my instantaneous tangent modulus. Then secant modulus. So secant modulus is like I take the first point and I take the last point. Okay, and using connecting these two point, whatever line I form, the slope of that line is known as secant modulus. Okay, so this is the point till which I am observing some linearity, above which I am deviating a lot from the linearity part. So connecting these two point will give me the secant modulus. And then this chord modulus. So chord modulus, like any two points in between, if I connect them and I calculate the slope, so that slope will be the chord modulus. Okay, so this is how we have four types of MOE of concrete. Okay, now how we determine the MOE of concrete in lab? Okay, this is like by definition how what is MOE and how we determine MOE. How we practically measure MOE in lab? So there are two methods. There one is known as static MOE, and another one is known as dynamic MOE. So first we will look at static MOE. So in this, MOE value is determined by uniaxial tension or compression loading. So I will take a concrete sample and I will load it under compression, or I will load it under tension, and based on the applied stress to the strain that has occurred inside the concrete, I will determine the MOE of concrete. So generally when we estimate static modulus of elasticity, we use compression load. Okay, so we have a concrete sample, we compress it due to the axial stress that we are applying, how much axial strain is occurring inside the concrete, that helps us to determine the MOE of concrete. Okay, so in statics test, what we do, we apply several cycles of unloading and loading and unloading on the sample prior to testing. Okay, so it is like we have a concrete sample whose ultimate compression strength we know it is PU. Okay, so during MOE, what we do, we apply a load in a smaller range of PU. Okay, because we don't want concrete to permanently deform. Okay, we want the elastic modulus of concrete. So we apply a concrete between load of PU by 9 to PU by 3. Okay, this in between this range we apply load on concrete. Okay, so you apply several cycles of loading and unloading. Okay, so what this several cycles of loading and unloading do? Okay, so they ensure that there is no creep or hysteresis effect in concrete, and whatever MOE value we are determining, it is accurate. Okay, so that is why we apply several cycles of loading. So what we do, we apply a load of PU by 3. Okay, we maintain it for some time, then we increase the load to PU by 9. We maintain it for some time, then we again reduce the load to PU by 3, then we again increase the load to PU by 9. So this is known as cycles of loading and unloading that we apply on concrete. Okay, now since we are operating in a middle range, okay, in some middle range between 0 to PU, the elastic modulus that we are determining from this test, it is known as chord modulus. Okay, now for conducting this test, there is a standard also which is there, which is ASTM C469. Okay, so what this code says, that the loading is applied in multiple cycles between PU by 3 to PU by 9 range, that as I told you here. Okay, and the loading rate remains constant at 140 kilonewton per centimeter square per minute. Okay, so this is the rate at which I need to apply load, and in between this range. Okay, so I will apply a load of PU by 3, maintain for some time, then I will go till PU by 9, and this loading rate will be 140 kilonewton per meter square centimeter square per minute. Then again the load will be reduced to PU by 3, then again it will be increased to PU by 9. So this is the cycle, multiple cycles of loading and unloading that we are doing. So you can see in the images here also how this test is performed. Okay, so this image is like taken from an actual testing setup of one of my samples for testing of modulus of elasticity in concrete lab in IIT Bombay. So in the first image you can see an extensiometer. Okay, so this is known as an extensiometer. Okay, so this extensometer, it is fixed on the surface of concrete. So suppose this is my concrete. So on the surface, I fix the extensometer on opposite sides. Okay, so and this is used to record the strain in concrete. So when I apply load on concrete, how much strain is occurring in concrete, I will be able to record by extensometer. Okay, whenever concrete is subjected to any load or we say stress. Okay, so this is the extensometer, and you can see behind this is a figure. This is a cylindrical sample on which here you can see extensometer is fixed on the concrete. Okay, and in the second image you can see the table of the software where we define the cyclic loading. So initially we have defined a preload of 25 kilonewton, just a small amount to stabilize the concrete under load, and then we apply multiple cycles of loading and unloading. So this is my pu by 9, and this is my pu by 3. So from pu by 9 I am going to pu by 3, then again I am reducing to pu by 9, then again I am going to pu by 3, and so on. So I have applied 4 cycles of loading and unloading, okay, between pu by 9 and pu by 3. Okay, so loading rate, you can see it is fixed for all the cycles, and I'm retaining each load for 60 seconds before increasing the load or decreasing the load. Okay, so this is the profile that we have defined as following ASTM C469 guideline. Now, here in the first figure, the top image shows the loading profile of what we saw in the figure previously. Okay, so this is my preload. Okay, then I'm going to PU by 9, then I'm increasing till PU by 3, then I'm unloading coming to PU by 9, then I'm increasing to PU by 3, then PU by 9, PU by 3, and so on. So we have 4 cycles of unloading and loading that we have applied. Okay, and the bottom image you can see the stress versus strain profile that is recorded. Okay, so there are three colors here. There is green, pink, and red. So green and pink are the two extensometers that we have fixed on the opposite side of the cylinder. So as I told you, one extensometer is fixed on one side, another extensometer is fixed on the opposite side, so that we can ensure that there is uniform stress applied to the concrete is uniform, so strain should be uniformly acting on the concrete. So that's why you apply two extensometers. Okay, so the green and the red pink lines, they show the extensometer reading, one from extensometer 1, green from extensometer 1, and pink from extensometer 2. Okay, and red shows the average strain from the two values. Okay, so you can see here from pu by 9, the load is increasing, stress is increasing to pu by 3, it is maintaining for some time, and then it is reducing to pu by 9, maintaining for some time, and then increasing. Okay, so initially there is some hysteresis effect which you can see here, permanent strain that has been left. Okay, but after 2 3 cycles that hysteresis effect gets nullified, and from that cycle we can measure the MOE of concrete. Okay, so if you see, if my concrete is flat, okay, and the stress applied is uniform on the concrete, then there won't be much difference in both the extensometer reading, and that you can see from here also. Okay, so this line, it shows the standard deviation, okay, between the two extensometer reading, and code says that it should be in the range of plus minus 20, but my case it was within the range of plus minus 5, which shows that both the extensometers are applied properly, and the stress distribution in the concrete was uniform, so whatever MOE I'm obtaining, it is accurate. Okay, because standard deviation is very small. Okay, if my surface is not plane, or loading is not axial, or extensometer is not attached properly, then the standard deviation value will be very high. Okay, then in such cases what we need to do, we need to stop the test, and we need to repeat the test by adjusting the sample, or by checking what is the problem with the sample. Okay, so this is how we determine the static modulus of elasticity. I hope anyone, do anyone has any doubt in the static modulus part, how this testing is performed? If you have any doubt, you can post in the chat box. Okay, now the MOE value corresponding to actual loading of concrete is known as dynamic modulus of elasticity. Okay, so instead of using a static load, we apply a longitudinal vibration, okay, on the concrete sample within the frequency range of 100 to 10,000 hertz. Okay, and this allows us to obtain a resonating frequency, okay, which depends upon the length of the sample, and which is equal to half of the wavelength. Okay, so from by supplying a longitudinal vibration in this range and by obtaining the resonance frequency, we calculate the modulus of elasticity using this formula, which is given in this code ASTM 251. Okay, so we have the length of sample, we have the density of the sample which is known to us, and we know the resonant frequency of the sample. Okay, so from this we determine the dynamic modulus of elasticity, and there is a code which standardizes the process how this testing is done. So if anyone wants to get a deeper understanding about the testing, you can follow this code. Okay, but mostly when we do testing in lab, we use the static modulus test only. Okay, this is one is rarely used to determine the modulus. Okay, so in ASTM code, this test is named as impulse excitation testing. Okay, where a little strike is done on concrete sample, and we measure the vibration response using sensors, and that we use to calculate the MOE of concrete. Okay, so using this test, we can evaluate the change in MOE value also with increasing concrete age, like you can see in this figure. Okay, with increasing age of concrete, how the MOE value of concrete is changing, that can be evaluated easily, because this is a quick test and a simple test. Okay, which doesn't require any extensive sample preparation or loading unloading profile. Okay, so for such cases, this test is preferred. Okay, or for practical application in real world conditions also, like for bridges, pavements, and high performance concrete, dynamic modulus elasticity will be a convenient way to move ahead. Now, there can be different types of MOE based on the direction of loading and the direction of deformation also. So the MOE value that we talked till now, it was known as longitudinal modulus or Young's modulus. Okay, so it is the ratio of axial stress to axial strain. Okay, when material is subjected to uniaxial loading. So this is my sample, this is my loading. Okay, and this is my deformation that is occurring. Okay, this is axial stress, this is axial strain. So MOE value that I get from this, it is known as Young's modulus. Then there is transverse modulus also, which is also known as shear modulus or rigidity modulus. So this is the ratio of shear stress to shear strain. Okay, so this was axial stress to axial strain. Then there is shear stress to shear strain when the concrete is subjected to shear loading. The shear loading will be like this. One end is subjected like this, one end is subjected like this, and there is a shear plane between. So the shear stress to shear strain will give me the shear modulus. Okay, and third is volumetric loading. So it is the ratio of hydrostatic stress to volumetric strain when material is subjected to uniform pressure from all directions. Suppose I have a sample which is placed in water. Okay, so there is pressure applied on the sample from all the sides, due to which there will be a volumetric strain developed in the concrete. Okay, so this ratio of this hydrostatic pressure to volumetric strain, this is known as bulk modulus of elasticity. Okay, so these are three common ways in which we define the modulus of elasticity of concrete. Now, how these MOEs are related to each other? So it is related by a factor which is known as Poisson's ratio. Okay, so this is my shear modulus, this is my Young's modulus. So they both have a relation. They both are correlated with each other with the factor which is known as Poisson's ratio. Okay, what is this Poisson's ratio? This is the ratio between lateral strain to longitudinal strain when the material is subjected to uniaxial stress. So this is my concrete. When it is subjected to stress, there will be an axial strain, and there will be a lateral strain also which will develop. So the ratio between this and this is known as Poisson's ratio. Okay, and it represents how material deform perpendicularly to the applied load when it is stretched or compressed. Okay, so this Poisson's ratio is nothing but strain in lateral direction, which is this direction, to strain in axial direction, which is this direction. Okay. Now, why there is a negative sign here? It ensures that Poisson's ratio is positive, since material typically contract laterally when stretched and expand laterally when compressed. So you can see here, when I'm applying a compression load, this is my compression and this is my elongation that is happening. Okay, so this will be positive, this will be negative. So just to make sure that Poisson's ratio is always positive, there is a negative sign that is placed in it. Okay, in this figure you can see all three types of strain under axial loading. Okay, so longitudinal strain, you can see it is increasing linearly and then it deviates from linearity. Volumetric strain, it increases at first and then it decreases. And lateral strain, it shows a very small increase initially and then its rate increases. Okay, so this is how different strains are there present in concrete and how they are related to each other. So here you can see volumetric strain can also be related to Young's modulus using this formula. Okay, so for relating any two modulus of elasticity, we need to know the Poisson's ratio. Now, how concrete affects the MOE? Okay, like how concrete property can affect the MOE of concrete. Okay, so first is the strength of concrete. Okay, so there is a formula that you will find in IS code or in general. MOE value is related to the compressive strength of concrete by this formula. MOE is equal to 5000 under root FCK. Okay, so MOE of concrete is directly proportional to the strength of concrete. It means that if we have a stronger concrete, it is stiffer and thus it has a high modulus of elasticity. Now in the figure you can see a stress versus strain profile for different systems. Okay, we have aggregates, we have cement paste, and we have concrete. So generally aggregate are stiffer in nature, so they show small strain at a applied stress level. Okay, suppose I am applying a stress of this level. Okay, so you can see aggregate shows a very small strain compared to cement paste, which shows a very large strain. Okay, and concrete will lie in between because it is a mixture of both aggregate and cement paste. Okay, so we can say that the proportion of aggregate and cement paste in the concrete also affects the MOE of concrete. So that's why second point is the cement paste. As porosity decreases, the MOE value of cement paste increases, so the MOE value of concrete will also increase. So if this curve will shift this side, then this curve will also shift upward. Okay, so MOE value will of concrete will also increase. Okay, aggregates, larger proportion and lower size fraction of aggregates results in higher MOE of concrete, because we know aggregates are stiffer in nature. So if we increase the proportion of aggregates, we'll make concrete also stiffer, so MOE value of concrete will also increase. Concrete moisture condition. So wet concrete shows higher modulus of elasticity compared to dry concrete. Why? Because as we talked in the last session, water is incompressible in nature. So when we apply a load on a saturated concrete, it will show higher stiffness compared to a concrete which is dry. Okay, that's why it has a higher modulus of elasticity. And fourth is the concrete age. Okay, so with age, what happens? Cement paste, it densifies. As cement paste densifies, it becomes stiffer in nature, and as cement paste becomes stiffer in nature, concretes also show stiffness. Okay, which increases the MOE of concrete. Okay, so this is how different factors in concrete affects the MOE value of concrete. Now, based on the discussion of MOE that we had just now, just try to answer these three questions. And in the meantime, if you have any doubt regarding any part that we have discussed in modulus of elasticity, you can ask. So any doubt regarding how we did like in that portion where I explained you the how we conduct the test of MOE. If you have any doubt with any part, you can ask right now. If there are no doubts, just try to answer these questions. So first question says a concrete mixture with higher aggregate stiffness and lower W by C ratio is expected to have what? Okay, so there are four options. Tell me the right option. So concrete has higher aggregate proportion and lower W by C ratio. What will be the correct answer? Yes, the correct answer will be A. So, as we saw just in the last slide, as the aggregate proportion increases, since aggregates are stiffer in nature, they increase the stiffness of concrete also. And as concrete stiffness increases, the MOE value of concrete increases. And W by C ratio lower. So, we know the relationship between W by C ratio and strength of concrete. Lower is the W by C ratio, higher is the compressive strength of concrete. If higher is the compressive strength of concrete, stiffer is the concrete, so higher will be the modulus of elasticity of concrete. Second, which of the following statement about volumetric modulus of elasticity of concrete is true? Okay, so there are four statements. You need to tell me which one is true for volumetric modulus of elasticity of concrete. So the last category that we saw, ratio of hydrostatic pressure to volumetric strain, that is known as volumetric elastic modulus. D won't be the correct answer. See, any kind of MOE value, it will increase at as it decreases as porosity of concrete increases. This one can also be a correct option. There are multiple correct options. Okay, this one is okay. So as porosity of concrete increases, we know that concrete will become weaker and it will be more, it will deform more. So modulus of elasticity will decrease. Okay. One more correct option is option B. Okay, which is more related to volumetric elasticity modulus. So we know that volumetric modulus, it is relates how material deform under uniform pressure, that is hydrostatic pressure. Okay, so when we are talking about uniform pressure, there is both bulk and shear deformation that has been taken into account. Okay, so that's why we say it accounts for both bulk and shear deformation, because it is a uniform deformation that is occurring from all sides. So which is bulk also, and there is shear deformation also. Okay, so volumetric modulus, it takes into account both longitudinal and shear modulus. Okay, or we can say bulk and shear modulus. Okay, so both option can be correct. Question number 3. If the Poisson's ratio of concrete increases, what is the expected effect on the transverse modulus or shear modulus? Can anyone tell me? Any more guesses? I received. I have seen one answer. One of you answered. So just think how Poisson's ratio is related to strain and how that strain is related to transverse modulus. Okay, so the correct answer is B. Okay, it decreases as lateral strain becomes more pronounced. So if you see this relationship, I will just copy this formula. So we know Poisson's ratio, it is the ratio of lateral strain to axial strain. So if my Poisson's ratio increases, it means that lateral strain in concrete is increasing. Okay. And we know transverse modulus, it is due to the lateral strain. Okay. So it means that concrete is undergoing more compression. Okay, means that concrete is undergoing more lateral expansion if lateral strain is increasing. So as lateral strain increases, the shear modulus, it will decrease, because modulus of elasticity is, it is inversely proportional to strain. So if this value increases, the elastic modulus decreases. So that's why B option is correct. Decreases at lateral strain becomes more pronounced. Okay, so just uh, during exam also, during practical application, just think how different factors are related to each other. Okay, if you are able to think about that, you will be able to go, reach the answer easily. Okay, so this was all about modulus of elasticity. Now let's move ahead. So next mechanical property that we will discuss is fatigue. Okay, so what does fatigue in concrete means? Okay, so fatigue in concrete refers to progressive weakening or eventual failure of a material when subjected to repeated or cyclic loading, even when stress applied is much smaller than the ultimate strength of concrete. Okay, so simply saying, if it is like I'm applying a load of concrete, say 30% of maximum load pu, okay, and I'm removing that load after some time, then I'm again applying the load, then I'm again removing the load, so on in a cyclic manner. Okay, so this cyclic loading and unloading, it causes weakening of a concrete structure over time, and this weakening of concrete structure over time, it is known as fatigue. Okay, so unlike a single overload failure, unlike a single overload failure, like unlike applying a load of pu, I'm applying a smaller fatigue damage. It accumulates over time due to repeated stress application, which leads to microcrack growth and eventual failure. So unlike applying a pu load, I'm applying a smaller load, 30% or 50% of pu, and I'm applying this load for a long period of time in a cyclic manner or in a slow loading case for a very long period. Okay, so when we apply such load for a long period, it causes microcracks to grow and eventually fail the concrete, even though we have not applied the ultimate failure load. Okay, so this is known as fatigue. Okay, now how this fatigue of concrete, failure of concrete happens in fatigue. Okay, so the failure process in is has three stages. Okay, first is the during the initial cycle, microcracks, they begin to grow near the itz of concrete. Okay, that has we have seen multiple times now. Now, as cyclic loading continues, what happens during the intermediate cycle? So this was initial cycles of loading, like point 0.3 pu we applied, then we removed, then we applied, then we removed. So in initial cycles, we will see microcracks will begin to form in itz. Then in intermediate cycle, after few initial cycles, what will happen? As cyclic loading increases, the microcracks, they will link up and grow, and they will show visible cracks. Okay, and as cracks will appear, concrete stiffness will start to decrease. And if stiffness of concrete starts to decrease, if E value decreases, then we know at the same stress, the strain will be more in concrete now. So there will be more deformation per cycle that will be happening in concrete. And finally, there will be a fracture or collapse of concrete after sufficient amount of cycle has been applied. When crack reaches critical size, concrete fails suddenly in a brittle manner and the structure collapse. Okay, so as we have discussed, fatigue can be of two types. Either loading is applied continuously but at a slow rate, or when it is applied in a cyclic manner. Okay, so the first one is known as creep fatigue. Okay, when we apply loading continuously but at a very small rate. And the second one, when we apply cyclic loading, that one is known as cyclic loading fatigue. Okay, so on this slide in the first figure, you can see how with increasing duration of creep fatigue loading from rapid loading. Okay, so this curve is rapid loading. Okay, and this is like, suppose rapid loading is happening in 1 minute, so I am decreasing the loading rate such that the loading is the applied load is one, I am applying the load at a smaller rate. Okay, so it is taking 3 minutes for failure to reach. Then I'm applying load at further smaller rate, then at further smaller rate, then at further smaller rate. Okay, so this is how I'm increasing the duration of testing by reducing the rate of loading. Okay, so you can see as the rate of loading decreases, you can see at failure, the strain in concrete continuously increases, and the failure stress of concrete is decreasing continuously because microcracks are getting more time to accumulate, to interact, and to merge with each other. Okay, so that's why with fatigue due to cracking in concrete, there is more deformation in concrete and the stress value of concrete reduces. And the second case you can see is the cyclic loading behavior. So I am applying load in different cycles. In this figure there is a cycle, first cycle, okay, and that is going through till 3,40,000 cycles. So you can see in the first cycle the behavior is perfect hysteresis effect that we saw in the earlier discussion. Okay, but as cycle increases you can see the strain that is there inside the concrete, it increases. So initially there was no strain in concrete, but after 3 lakh cycle there is a lot of strain that is there inside the concrete that has developed due to multiple loading cycles. And during loading also there is a lot of strain that is occurring in concrete, okay, for the same peak load. Okay, suppose this is zero point 0.3 pu. Okay, the strain in concrete that is happening during loading is also a lot. Okay, and there is a leftover deformation that will continuously add up. Okay, and this will eventually lead to failure of concrete, okay, due to fatigue cracking. So this was about fatigue. Okay, what is fatigue, what are the stages of fatigue, and how many types of fatigue are there in concrete. Now, after fatigue, we have bond strength of concrete. Okay, so bond strength of concrete refers to the adhesion and the mechanical interlock between reinforcement steel and concrete. So, when we talk about reinforced concrete, we have rebar embedded in concrete. So, the bond strength of the interface between the strength at the interface between rebar and concrete, it is known as the bond strength of concrete. Okay, so importance of bond strength we can understand from the basic design principle of reinforced concrete also that we discussed in IS 456. So they play a crucial role in load transfer, crack control, and structural integrity. I guess there was some network issue or something. Please repeat fatigue. Can you tell me at which point you encountered? Was my screen not visible or was there some problem? Okay. At what point you want me to repeat? So on this slide, I was talking about what is fatigue. Okay, fatigue is like I'm applying a smaller quantity of load but for a longer time. Okay, so when I apply a small load but for a longer time, the cracks they accumulate over time due to repeated stress application, and this leads to failure of concrete. And this failure is known as fatigue. Then we talk about different stages of fatigue. So at initial cycles, micro cracks forms. At intermediate cycles, these cracks they grow up and link together. And finally, once there is enough cracking in concrete, we see failure and collapse. Okay, this was what I talked on this slide. And on the second slide, I told you about different types of fatigue. So there can be two cases. Either I am applying a load at a very small rate continuously, or I am applying a cyclic loading. Okay, so I am applying a pu by 3 load, and I am removing, then applying a pu by 3 load, then removing. So like that. Okay, that is cyclic loading. And creep fatigue is I am applying pu load only, but at a smaller rate. So code says that we need to apply load at 140 kilonewton per centimeter square per minute. But instead of that, suppose I am applying load at 1 kilonewton per centimeter square per minute. So at a very small rate. So at such in such conditions, what happen? There will be a lot of strain that will be developed in concrete before failure, and the failure load will be also be lower compared to rapid loading, which was at 140 kilonewton per centimeter square per minute. Okay, so this is known as creep fatigue, and the second one is known as cyclic loading fatigue. So in cyclic loading, what will happen? After each cycle there will be some permanent deformation in concrete. That deformation will accumulate over time, and then with increasing amount of cycle, the strain that is occurring due to loading, it will also increase, and eventually there will be failure of concrete that will happen. Okay, even though my load that I have applied is zero point 0.3, 30% of peak load only, but still due to growing crack within the concrete, failure can still occur in fatigue. I hope it is clear now. If you still have any doubt, you can wait till the end of the session. We can discuss it again. Okay. And I request everyone, like, suppose in between there is a connection flaw or my screen is not visible, just unmute and speak whenever connection gets back, so that I know there was some problem. Because when I switch to slideshow mode, I can't see whether my network was lost or not. Okay, so on this slide, we are discussing about bond strength of concrete, which is the strength at the interface between steel and reinforcement. So, importance of bond strength we can understand from the basic design principle of reinforced concrete as per IS 456 also. So, if you see the design of concrete, design of reinforced concrete beam under bending, so we say that this is my section, okay, and these are my reinforcement. Okay, so at this level, under applied stress, whatever strain is there in concrete is same as the strain that is there in steel. Okay, so this is one assumption that we take when we design a reinforced concrete as per IS 456. Okay, at same cross section level, the strain in concrete and steel are equal. This is only possible when we assume that there is a perfect bond between steel reinforcement and concrete, which allows proper stress transfer through interface. And that's why bond strength of reinforced concrete is an important aspect when we talk in terms of design. Now, there are three primary mechanisms which governs the bond strength of concrete. First is adhesion between the cement paste and the reinforcement surface. Second is friction, which results due to the resistance developed by the roughness of the reinforcement surface and the concrete when we apply some pull on the rebar. Okay, so that is the frictional resistance at the interface. And third is the mechanical interlock, which is due to the physical engagement of the ribs at that are present on the reinforcement and the surrounding concrete. So when we talk about rebar, they have ribs over them. Okay, so this is kind of rib. So when we apply a load, this rib will also try to resist the pull. Okay, so that is known as mechanical interlock. So there will be concrete here, there will be concrete here, this is the ribbed steel part. So when we apply a force, they will also provide some resistance. They are mechanically interlocked with concrete, which will prevent their slippage. Okay, and it will improve the load transfer at the interface also. Okay, so when we talk about bond strength of reinforced concrete, it is due to all the three things. It is due to the chemical adhesion between the cement paste and the rebar surface. It is due to the friction between the rebar surface and the concrete, and it is due to the mechanical interlock due to the presence of ribs. Okay, now there are three main factors that can affect the bond strength of concrete. First is the compressive strength. Okay, so as compressive strength increases, the addition of cement paste with reinforcement, it increases. Okay, as paste content increases, so the bond strength increases. Second is the reinforcement type and surface texture. Okay, so if we are using a coated rebar, suppose this is a rebar and over rebar I have done a epoxy coating. Okay, so what this does, this epoxy coating, it reduces the friction of the rebar surface, because epoxy materials, they are generally smoother compared to steel, bare steel surface. So due to this, the frictional resistance that the rebars were was offering to the pull forces, it reduces. Okay, so bond strength decreases in case of coated reinforcements. Then the last is the reinforcement diameter and development length. Okay, so as both these entities increases, the adhesion and the mechanical interlock with the concrete increases. Okay, so as diameter increases, okay, then also the bond strength between concrete and rebar increases. And as the development length increases, development length is the embedded length inside concrete. So this length, if this increases, then also the mechanical interlock force, the chemical adhesion force, they all increases. Okay, so the bond strength increases. Okay, so these three are the critical factor that defines the bond strength of concrete. So here you can see the bond strength of how bond strength of concrete is determined. So this is again from one of my setups in concrete lab here in IIT Bombay. So in the first figure you can see this is known as a universal testing machine, UTM. Okay, where I have a pull out frame. So you can see this frame, this is known as a pull out frame. Okay, so this frame has a hole at the bottom. Okay, and through that hole my rebar is passing and it is gripping here. Okay, and the top end of the pull out frame is gripped at the this portion. Okay, and I have my concrete placed inverted. So this is how my concrete is. Okay, this is my concrete. I have placed it inverted. Okay, so this is my concrete and the rebar that is there inside the concrete, it is gripped here. And while this frame is made to be fixed, stayed static using this top grip. Okay, so now when I will apply a pull out force on the sample, what will happen? Since this frame can't move and the rebar is getting pulled. Okay, so rebar, the bond strength between rebar and concrete will be, we will be able to determine the bond strength between rebar and concrete. Now how we see how much slip has occurred of rebar when this force is applied. So for this I have attached an LVDT at the top. So this is known as LVDT. Okay, it helps us to record the strain or the slip in the rebar. Okay, so there is a small portion of rebar that is coming out of concrete over which I have placed the LVDT. So as the rebar will move slip downwards due to applied load, this uh, probe will go inside the concrete, and this movement of probe I am recording as slip. Okay, so here you can see as the stress applied on the concrete increases, the slip it increases slowly, and then after an ultimate stress value, the bond between the steel and the concrete it fails, and we record a lot of slip because now there is no adhesion between steel and concrete and rebar is free to move. Okay, more free, like rebar is has more freedom to move. Okay, so as loading increases the bond stress increases, then after a peak as stress exceeds the strength of the bond fails and we see a large slippage that is occurring in the reinforcement, and this is the kind of failure that you see at the end. Okay, once the bond has failed. Okay, so there is cracking in the cover concrete and this rebar is now free to move out. Okay, so this data is like showing two concretes, okay, two reinforced concrete, one after 7 days of curing and one after 28 days of curing. So we know as curing age increases, the compressive strength of concrete increases. So you can see the peak bond strength is also increased, okay, because of increase in chemical adhesion between the concrete cover and the reinforcement surface. Okay, so this is how bond strength testing is done for concrete. Now, based on your understanding about fatigue and bond strength, just try to answer these questions. And in the meantime, if you have anyone of you has doubt regarding fatigue or bond strength, you can ask. So, question number 4 says, which of the following condition will increase the fatigue life of concrete the most? So, when we talk about fatigue life, it means that after how many cycles of fatigue loading concrete is failing. So if a concrete is failing after 50 cycles and if second concrete is failing after 100 cycles, then we say that fatigue life of second concrete is more because it is able to take more number of fatigue cycles before failure. Yes, no, A won't be the correct answer. Increasing W by C ratio. If we'll increase the W by C ratio, the strength of concrete will reduce. So it may deform more under load. So fatigue life may decrease instead of increasing. Just think about how a concrete will respond to stress application. So whatever we discussed in MOE, fatigue is like repeated MOE. Like we are applying a certain in between load but repetitively. Okay, So if my compressive strength of concrete is small, it will undergo more deformation after each cycle. So eventually, at lower fatigue cycles only, there will be so much deformation in concrete that the concrete will fail. Instead of increasing the fatigue life, it will decrease the fatigue life. Yes, the correct answer is B, using well-graded aggregates and reducing porosity. Okay, so well-graded aggregates, they will improve the concrete density and it will reduce the micro cracking in concrete. Okay, that will increase the fatigue life. And lower porosity, it ensures that there is no stress concentration in concrete, or concrete strength is higher. Okay, so amount of deformation after each cycle will reduce. Okay, so eventually fatigue resistance will increase, fatigue life will increase. Question number 5. When comparing fatigue failure to normal strength concrete and high strength concrete, which of the following statement is correct? So suppose you have two concretes. One has a compressive strength of 25 MPa and another one has a compressive strength of 55 MPa. So how their fatigue failure will compare to each other? Yes, the correct answer is A. Okay, so normal concrete has shorter fatigue life because it is weaker in nature. It has weaker ITZ. Okay, so it is more susceptible to fatigue failure. Whereas high strength concrete, it is more denser. Okay, and it has less porosity, so it will provide more resistance to fatigue. Okay, and it will have a higher fatigue life. Question number 6. What is the primary mechanism responsible for fatigue failure in high strength concrete? So in high strength concrete, what will be the failure mechanism in fatigue? No, A won't be the correct option. Just think more. We are talking about high strength concrete. Okay, so strength of cement paste will be higher because we are using silica fume or fly ash in our mixture, which will increase the strength of the cement paste. Okay, so failure doesn't happen at in the paste. Okay, the correct answer is B. Okay, ITZ. So in high strength concrete also we know ITZ is the weakest link. Okay, so when we apply repeated cycles of loading, gradually this ITZ zone will deteriorate. Okay, and that will cause failure of concrete in fatigue. Okay, so the fracture that is occurring, it occurs at the ITZ, not in the cement paste. Okay, the micro cracks that are growing, they will grow extensively at the ITZ, which will lead to failure of concrete in fatigue. Then these two questions, okay, regarding bond strength. So question number 7 is, in pull-out test, a smooth rebar is embedded in a high strength concrete. It fails. Why it fails? What is the reason why a smooth rebar embedded in high strength concrete fails? What is the mechanism of failure? Or we can say flails prematurely. So I wanted a bond strength of 10 MPa, but when I used a smooth bar embedded in concrete, I found a bond strength of only 5 MPa. So what can be the reason that it fails prematurely? Can anyone tell me what can be the mechanism which has dominated here?
Adhesion failure in the between the cement paste and the rebar.
Yeah, the correct
That is
answer is
friction. Yeah.
adhesion failure. Why? Because I have
Yeah.
a smooth bar. Okay, so when I have a smooth surface of the rebar, what will happen? The adhesion of the rebar with the cement paste, it will be a problem. Though we have a dense concrete, okay, we have a high strength concrete which will have a dense cement paste, but smooth bar surface, it will reduce the adhesion. Okay, when there are pores at the rebar surface, when there is friction that is present on the rebar surface, when there is rough texture, those rough texture, they bond more with the cement paste, like we discussed with aggregate cement bond. The roughness of the aggregates, it increases the bond with the cement paste. The similar concept applies with the reinforcements also. A rough surface rebar will bond better with the concrete, inside the concrete, rather than a smooth bar. Okay, so that's why adhesion failure is governing the failure here in bond strength, because this will slip, okay, at a lower strength only. Mechanical interlock, it may not be affected because mechanical interlock is determined by the presence of ribs. Okay, so either in smooth bar or deform rough bar, if there are ribs present, so mechanical interlock will be there. Though due to smoothness, that interlock value will also reduce, but the main culprit is the adhesion here. Question number 8. Bond strength between reinforcement and concrete significantly decreases when? So, in what case the bond strength of concrete will reduce? No, if I'm using a low W by C ratio, the strength of concrete will increase. So, if the strength of concrete will increase, the adhesion between the cement paste and the rebar will increase. So, bond strength should increase rather than decreasing. Yes, the correct answer is epoxy coated, when epoxy coated rebars are used. So, what is the problem with epoxy coated rebars? It is the coating. So, what the coating does, it makes rebar smooth, rebar surface smooth. So, as the rebar surface becomes smooth, the adhesion between the cement paste and the rebar, it decreases. So, the bond strength between reinforcement and concrete, it decreases significantly. Okay, so just remember these three things: adhesion, friction, and mechanical interlock. Sometimes adhesion and friction are, they can talk together, but mechanical interlock is the ribs, presence of ribs. Okay, so these three are the key factor which determine the bond strength of concrete. Okay, so let's move ahead now. And the next topic in hardened property of concrete is creep in concrete. So what does creep mean? So if we simply say creep is a gradual long-term deformation of hardened concrete under sustained load, which cause increasing strain without change in applied stress. So this is similar to what we talked in fatigue loading here. Okay, creep fatigue. Okay, so we are applying a load of say pu by 3. Okay, but for a very long time we have applied this load. Okay, so when we apply a load for a very long time, okay, it increases the strain in concrete without any change in stress that is applied. Okay, and this is known as creep. Okay, so this load may not be even around the pu. Okay, so we know pu is the failure load, but we are applying a very small load, pu by 3 or pu by 5. Okay, it is nowhere close to pu, but still there can be failure in concrete due to sustained loading action, which results in deformation in concrete. So, as written in the second point, you can see it occurs as slow, continuous movement within the material, which leads to progressive change in the shape over time. So, the micro cracks that are growing inside the concrete, they will continue to grow at this loading level also, and there will be continuous deformation that is occurring inside the material. The cracks are growing slowly, slowly. They are interlinking. They are growing in shape, and eventually they will lead to failure of concrete. Now, what is the end result? So this creep phenomena, it affects the structural stability of concrete by affecting the dimension and the internal stress distribution. So an example of creep action you can see from the image here also. Okay, so here we have a bridge deck, okay, which is under continuous load, okay, on the top. So in this loading, they you can see there is a small deflection, vertical deflection that you can see here due to the loading, and this is known as creep deflection. Okay, where the beam has deformed over time. So initially beam was like this, but due to loading it has deformed. Okay, and this is known as creep deformation. Okay, deformation due to sustained loading. Now the same thing we can understand from the stress strain relationship also here. Okay, so under a constant applied stress of sigma naught, okay, this sigma naught is very very less than the ultimate stress. Okay, so after a time t naught, okay, I'm applying a sigma naught stress, and this is continue constantly applied. Okay, so under this stress what happens, there is continuous increase in strain. Okay, so initially there will be some elastic strain. Okay, that is due to the elasticity, modulus of elasticity of concrete. Okay, so sigma naught upon epsilon, sigma naught upon e will give me the initial elastic strain. Okay, so as soon as the load is applied, there will be some elastic strain that will occur in the concrete. Okay, now when this load is retained over time, what will happen, slowly slowly the strain in concrete, it will increase. Okay, and after a time t, you can see there is more strain in concrete compared to what there was after time t naught. Okay, so this increment in strain between that happened between t naught and t, it is known as creep. Okay, that is the difference between the long term strain and the elastic strain. Okay, so creep we defined like this. Okay, creep is total strain minus elastic strain. Okay, this is creep. Now what happens when I remove the load? Okay, so this process known as relaxation or creep recovery. So when the continuous load is removed, the strain decreases immediately. So this immediate decrease, okay, you see here, there this was elastic strain, then this is the due to continuous loading, the creep that occurred. Okay, and at this point I remove the load from the concrete. So what will happen, there will be some elastic recovery based on the strength of concrete at this point. Based on the MOE value of concrete at this stage, there will be elastic recovery. That will be the elastic strain that will recover. Once this elastic strain has recovered, okay, there after this there will be some recovery in the creep strain also that will occur. Okay, but a lot of portion will remain irreversible. Okay, after loading is applied. So this quick recovery, the quick elastic recovery, it is followed by continuous decrease in strain. And this decrease in strain that has occurred, this is known as creep recovery. Okay, and at this point of total creep strain suffered by the concrete. Okay, so this is the total strain that concrete has suffered. Out of this there is a elastic recovery and there is a creep recovery. If I subtract the elastic and the creep recovery, the remaining part is known as the irreversible creep that won't recover. Okay, and that is this creep is due to the permanent deformation in concrete that has occurred due to cracking. Now, this deformation in concrete that we are talking, it happens in three stages. Okay, so creep has three stages. First is primary creep. Okay, so there is an instantaneous strain, then there is a rapid growth in strain. Okay, okay, that is there. That happens and that continues to slow down. So that is known as primary creep. Then there is secondary creep. Okay, where the rate of increase of strain, it is almost the same. Okay, strain is increasing at a uniform rate. Okay, so here you can see there are cyclic loading and unloading cycles also, okay, which can combine together. Okay, and then there is ternary creep. Okay, so in ternary creep what happens, the creep strain, the rate at which the creep increase it also increases. Why? Because there is extensive cracking in concrete. So at the same loading, since the MOE value of concrete has reduced, there will be more strain that will generate inside the concrete. So creep rate also increases. Okay, so that's why there are three cycles. There is primary creep, there is secondary creep, and there is ternary creep. In primary creep, the creep rate decreases. Okay, after an initial shoot. In secondary creep, the creep rate remains the constant, and in ternary creep, the rate of creep increases. Now, we have seen what creep is and how creep causes deformation in concrete. But it is important for us to understand why creep is occurring in concrete. So there are two hypotheses that has been proposed to understand creep in concrete. So first hypothesis, it explains concrete creep, and this was given by Fresinet, a scientist named Fresinet. Okay, and he made this observation. He made this hypothesis based on his observation of deformation of a Plogastel bridge in France. So he saw how this bridge was deforming, and based on the deformation pattern of this bridge, he made an hypothesis of what is creep. And this he did in 1926 to 1929 period. Okay, so according to Fresinet, the creep is just shrinkage amplified by applied stress. Okay, so his theory says that loss of water through drying is greater in loaded concrete than in free concrete. So for him, suppose this is the concrete and applying a creep load. So what happens? There is water inside the concrete. Okay, so under applied load, what happens? There is drying of water, loss of water from inside the concrete, and this is creep according to Fresnel. This the shrinkage that is occurring due to loss of water. This is creep, and this has intensified, amplified because of the presence of applied stress. So if there is no stress, this loss of moisture will occur at a smaller rate. But since we have applied some stress on concrete, the loss of moisture is occurring at a higher rate. So shrinkage of concrete is occurring at a higher rate, and that is known as creep of in concrete, according to this scientist president. Then another scientist named Lyman in 1934, he suggested that creep failure can be due to three reasons. Okay, it can be due to crystalline sliding of CSH, it can be due to movement of adsorbed water in cement hydration, and it can be due to viscous flow. Okay, so all causes of creep that has been proposed till date, till 2026, okay, it can be included in one of these three types. Okay, so if anyone wants to dig deeper into what they have said in their theories, okay, what these two researchers have said, so you can refer to their article. So I have provided the link of their article on this slide. You can search this article on Google, you can read that article, and then you will get a more clear understanding of what all things they have said in their theories. So if we try to understand the second theory, the Lyman theory, okay, of who says that there are three possible causes of creep. Okay, so what he says that in a time dependent deformation of concrete, there are multiple activities that are occurring. There is viscous flow of water in gel pores. Okay, so we know CSH, concrete contains CSH gel, and there is gel water inside the capillary pores. So under sustained loading, this water gradually is forced out of gel, and loss of water from the gel pores, it causes deformation over time. Okay, and this is one of the reason of creep in concrete. So this component is reversible in nature. So some of the part of this component can be recovered. Okay, when the loading is removed. Then second is micro cracking and stress distribution. Okay, so under sustained loading, we have seen that micro cracks, they will grow at ITZ. Okay, and these cracks, they propagate over time, which cause the permanent deformation. And even so, if we remove the load, this strain can't be recovered. So that's why this is known as the irreversible part of creep. And third is the sliding and rearrangement of CSH sheets. So we have CSH layers. Okay, and we have read that CSH, they are held by weak van der Waal forces. So when we apply stress on concrete, so this weak van der Waal forces, they allow sliding of CSH sheets across each other. Okay, and due to this sliding, there is deformation in concrete, which results in creep in concrete. And this again is irreversible in nature. Okay, so these are the three things that Lyman he said that can be a possible cause of creep in concrete. Okay, I hope no one has any doubt in the creep section we have discussed. Yes. Okay, now there can be different ways in which concrete can affect the creep of concrete. So it is again the same discussion that we have done till now for fatigue or bond strength or MOE. Okay, so if we see from material point of view, first is the aggregate. So okay, so aggregates, they undergo very little creep. Okay, it is the paste that is responsible for creep. Why? Because aggregates are stiffer in nature. Okay, while paste is weaker in nature. So we saw the MOE profile, okay, of stress versus strain. So aggregate has higher stiffness, paste has smaller stiffness. Okay, so if we use stronger aggregates, aggregates can create more restraining effect, okay, and it can lower the creep in concrete. Because of high modulus of elasticity aggregate, it lowers the creep in concrete. Okay, so it is said that if we increase the aggregate proportion from 65% to 75%, we can reduce the creep in concrete by 10%. Okay, then we have paste. So we have, as we have discussed just now, it is the paste that is responsible for creep in creeping effect in concrete. So the quality of paste and the amount of cement paste in a concrete, it can influence a lot. Okay, so if you have a poorer paste structure, it can undergo higher creep. Okay, that's why we say creep increases if we increase the W by C ratio, because as we increase the W by C ratio, the amount of paste inside the concrete, it increases, so there is chance for more creep inside concrete because there is more moisture available that can be lost under deformation. Then influence of age. So as the concrete ages, the cement paste densifies. Okay, so the quality of paste improves, so creeping effect decreases. So you can see here, as the age of concrete increases, the relative creep inside the concrete, it is continuously decreasing because of denser microstructure of concrete. Then fourth is the dimension of concrete, which is very important factor. Okay, and that is defined by volume to surface area ratio. Okay, so for higher surface area concretes, like for thin section or small elements, there is more creep. Why? Because there is more exposed surface area that is available, which allows more moisture loss. Okay, so if there is greater moisture loss, there is higher creep deformation. Okay, similarly, if I have a lower surface area to volume ratio, then there is lower creep because most of the moisture is trapped inside, and since surface area is small, the loss of moisture will also be small, so creep will be low. So generally in massive structures like dams and thick walls, we don't see creep as much of an issue. But in slabs or small beams, the creep is a issue where surface area is high. And you can see from this diagram also, as the volume to surface area ratio is increasing, okay, the creep is reducing because surface area is reducing. Okay, so at lower volume to surface area, you can see there is higher creep in concrete compared to at higher volume to surface area ratio. And with age of concrete also, the creep decreases because my cement paste, it densifies. Okay, so both things you can understand from this figure. Then there is relative humidity. So at low relative humidity, what will happen? Drying of concrete will be faster, so creep effect will be faster. So you can see, as the relative humidity of the environment increases, the creep effect decreases. Then the way in which we have cured the concrete also can determine the creep effect. Okay, so if we are cured the concrete at normal temperature, and if we have cured the concrete at elevated temperature, and we have dried concrete before testing, okay, so they will show more creep because of weak microstructure. While if we have cured concrete properly, it has a more stable microstructure, so it reduces creep deformation under loading. Okay, so our curing also determines the creep. Okay, more dense is the microstructure of concrete, higher is the strength of concrete, lower is the creep in concrete. Now just try to answer these three simple questions related to creep. Okay, and if anyone has any doubt regarding creep and what is creep and how different factors are affecting creep, you can ask. If not, tell me the answer for question number 9. What is the primary reason why high strength concrete exhibits lower creep compared to normal strength concrete? Can anyone tell me the answer for question number 9? So we have just now discussed different factors which affects the creep of concrete. So thinking about those factors, how strength of concrete is determined affecting the creep? Yes, the correct answer is B. So, in high strength concrete, we have a denser cement matrix. We have lower porosity at ITZ, and we have a stronger paste aggregate bond. Okay, so all these factors they reduce the creep in concrete. Okay, so under sustained loading, there will be less deformation in concrete because of denser microstructure. Question number 10. Which environmental condition accelerates creep the most? Okay. So suppose you have placed a concrete into different environment. All concretes are the same. So which environmental condition will accelerate the creep? Can anyone tell me the answer for question number 10? I'm talking about acceleration of creep. Okay. So B won't be the correct answer. At low temperature and high humidity, if there is high humidity, then moisture loss will be lower. Okay, it won't be higher. So correct answer is A, at low relative humidity and high temperature. Okay, so low relative humidity and high temperature, it will accelerate the moisture loss from inside concrete. Okay, and as moisture loss will increase, the creep strain will increase because there will be shrinkage in concrete. Okay, so think about the first theory that we talked for Fresinet. Okay, he what he said, creep is nothing but loss of moisture from concrete when it is in loaded condition. Okay, so if loss of moisture increases, then creep also increases, and loss of moisture will increase when concrete will have higher temperature or it will have lower humidity. So lower humidity, it accelerates the evaporation of moisture from concrete. Question number 11. Which factor has the most influence on long term creep in concrete? So, out of these four factors, which factor will influence the long term creep in concrete the most?
Is it C, rate of loading?
Uh, Rate of loading is constant. Like when we talk about creep loading, we are not increasing the rate. The rate is kept constant, loading is constant. It is the time for how much time we have kept the concrete under loading. It is like sustained load. Load is not changing, it is maintained. The correct answer is A, W by C ratio. Okay, how? So a higher W by C ratio, it will increase the porosity in concrete. Okay, and this will lead to higher creep because now there is more water inside, there is more moisture inside concrete. So under an applied load, the moisture movement will be increased. Okay, and the paste structure will be weakened. Okay, so my creep effect will be more. Okay, so in long term, you can also think about evaporation loss, the effect of temperature or relative humidity. They will come into account when there will be more moisture inside concrete, and that is the case of higher W by C ratio. So higher W by C ratio, it will undergo more deformation also. Why? Because it has lower strength. Okay, so generally for all mechanical properties that we talk about, be compressive strength, tensile strength, bond strength, fatigue, creep, shrinkage, all of them are primarily dependent upon the compressive strength of concrete, and compressive strength of concrete is significantly influenced by the W by C ratio. Okay, so this is something that is very important to remember. Okay, W by C ratio, how it is affecting the concrete microstructure and how that microstructure is affecting different properties of concrete. Okay, now Next thing is how we can predict or measure creep. Okay, so till now we have talked about what is creep and how creep deformation occurs and how different concrete factors are affecting the creep in concrete. But how we measure the creep in concrete? Okay, so for first we'll look at prediction of creep. Okay, for this we have ACI 219 model. Okay, so by prediction we mean estimation of creep in future. Okay, so depending upon whatever the state we have in present, if we know that we are applying this much amount of load for these many years, okay, what will be the creep after suppose 28 years or 30 years? So that is known as prediction of creep. So there is a method that is standardized by ACI 219 model for creep prediction, and this is an empirical method which is used to estimate creep strain in concrete over time. And this method is this model that they have developed. It is based on experimental data, and it considers factors like time, humidity, and mixture proportion of concrete. So, when we are talking about quantifying creep in concrete, there are two terms that are commonly used. First is the creep coefficient, and second is the compliance function. So, creep coefficient is the common description for the description to express creep behavior in concrete, and it is nothing but it is known as the creep strain upon elastic strain. Okay, so we saw this profile. This is elastic strain, and this is remaining strain. Okay, so this is known as strain due to creep. Okay, says epsilon cr, and this is known as strain due to initial modulus of elasticity of concrete, and this is total strain that has occurred in concrete. So the ratio between creep strain to elastic strain, it is known as creep coefficient. Okay, so weaker concretes will have higher creep coefficient, a denser and a stronger concrete will have a lower creep coefficient. Okay, and second is the compliance function, which is again an expression of creep. Okay, and it is defined as strain per unit stress. So total strain, that is creep strain plus elastic strain, depend upon what is the sustained loading that we have applied. Okay, so suppose I am applying a 30 kilonewton load. Okay, 30 MPa stress on concrete, and this is sustained for 15 years. Okay, so what is the total strain in 15 years? That is epsilon t, and sigma naught is my 30 MPa. Okay, so the ratio of strain to stress gives me the compliance function. Okay, and these two parameters, they are commonly used to define creep in concrete. Now, as per this ACI method, the creep coefficient after a time t under loading, okay, can be given by this formula. Okay, so at time t naught, okay, at time t, okay, suppose at time t I applied uh, at time t naught I started applying load on concrete. Okay, so this is the stage at which I applied sustained stress on concrete. Then after time t, okay, so this is suppose 1 year. Okay, and then this is 15 years. So if I know at 1 year I applied some strain on concrete, so after 15 years how much, what will be my creep coefficient? So that is given by this formula. So t naught is the age of concrete at loading. Okay, and epsilon u, this say mu nu, uh, epsilon mu is the ultimate creep coefficient. Okay, so how we get the ultimate creep coefficient? For this ACI has given this formula. Okay, so there are different factors: gamma ct naught, gamma rh, gamma vs, gamma s, gamma fa, gamma a. Okay, so these all factors, they have proposed equation. Okay, and these all factors, they determine how creep is related to loading condition, how creep is related to relative humidity, volume to surface area ratio, slump factor, fine aggregate content, and air void inside concrete. Okay, so from this formula we can get the ultimate creep coefficient. Once we know the ultimate creep coefficient, then knowing for how much time we have kept the concrete under loading, we can determine the creep coefficient after a time t. Okay, so for this they have given this formula. So we'll see the application of this formula shortly when we'll talk about one numerical. Okay, So for each of the factor, we have this table which is there, which helps us to derive the this ultimate creep coefficient. So for moist curing, what will be the creep coefficient? What for steam curing, what will be the factor? Then for different RH, there are different factors that are given. Okay, then for volume to surface area ratio, how we calculate the factor, it is given. For slump, there is a factor. For fine aggregate proportion, there is a factor. For air void content, there is a factor. Okay, so like this, there are different factors that are defined, okay, which can affect the creep of concrete. So this was ACI method. Then there is BS method also. Okay, British Standard Method also. So here we first need to determine the MOE of concrete. So after a time T naught, they have defined an equation how MOE of concrete can be determined if we know MOE after 28 days of curing. Okay, so after T naught age, what is the MOE? For this, they have given this equation. Okay, then strength ratios there are given. Okay, it is zero point 0.7 for 7 days, 90 days it is 1.7, and for 1 year it is 1.25, these ratios. Okay, once we know the MOE of concrete, in British Standard there is a chart that is given that helps us to calculate the creep coefficient. Okay, so uh, we need to know three factors here. We need to know the MOE value of concrete, we need to know the volume to surface area ratio, we need to know the RH of concrete, and we need to know the age of application of load. Okay, so suppose and there are three columns here. For volume to surface area ratio, below 100 we need to use this scale, between 100 to 200 we need to use this scale, and above 200 we need to use this scale. So suppose my volume to surface area ratio is 150. Okay, RH is 50%, concrete age is 20 days. Okay, so what will happen at 50% RH? First, I will draw a vertical line, then I will check how it is, where it is interacting the age of application of load. Okay, so at 20 days of age, I applied the loads. Okay, so this is my age of concrete. From here, I will draw a horizontal line, and then I will use the second chart. Okay, and I will see where this line is interacting. So it is interacting between 2.2 to 2.4. So my ultimate creep coefficient, it will come out to be 2.3. Okay, so this is the British Standard Method for predicting ultimate creep in concrete. Okay, and this was ACI method of determining ultimate creep and then determining creep at any intermediate age. Okay, so this is how we predict creep. Now how we measure creep. Okay, suppose at that was prediction, so we know for this much amount of time we are loading concrete, so what can be creep in future. But suppose now on site or in lab I want to measure creep, actually measure creep. So for that there is ASTM C512 method. Okay, so it accounts for moisture loss, age of loading, stress level, and curing condition. Okay, for determining creep. Okay, and we can determine creep either using a cylinder of 500 cross 300 dimension or using a prism. Okay, so what this method says, first you determine the MOE of concrete. Okay, then you keep the concrete under 30 to 40% loading in a creep frame. Okay, load the concrete for a month or a year while keeping the environmental conditions stable, and record the deformation of concrete after different interval. So creep strain will be nothing but total strain minus elastic strain. Elastic strain I can get from MOE. Okay, so I know how much loading I have applied and I know the MOE value. Okay, so that will give me the elastic strain, and I am recording total deformation over time, so that will be my epsilon t, so I can record creep strain over time. Okay, once I record the creep strain, I can determine the creep coefficient also. So this is how we do in lab. Okay, and this is the setup. Okay, so you can see this frame. Okay, this is the top part, this is the bottom part with spring, and these are concrete samples. Okay, and these concrete samples, they are loaded under a constant loading support. Okay, and we are measuring the deformation in concrete over time, so that deformation will be ultimate total deformation. That deformation will give me the total strain, and from that I can determine the creep strain. Okay, using a deflectometer, we record the deformation or strain, and then we calculate the creep strain. Now, this was when a single load is applied. So till now, what we have talked, that this is a cylinder and there is a single load of PU by 3 that is applied on the concrete. What if there are multiple sustained loadings are there? So suppose there is PU by 3 load that has been there acting for 1 year. Then there is some other PU by 9 load that is acting on the same concrete since 5 years. There is again one PU by 12 load that has been acting on concrete since 10 years. Okay, so what will be the cumulative damage due to this multiple loading condition? So for that we have minor rules. Okay, minors rule. Okay, so if multiple loading are acting on the same concrete, then failure due to creep deformation is given by linear damage rule or minor Palgren rule. Okay, so this rule was first proposed in 2019-24, and then it was further developed by Miner in 1945. Okay, so what this rule says, that fatigue damage based on multiple cycles of loading can be calculated by the ratio of number of cycles at that stress level to total number of cycles for failure. Suppose this PU by 3 load, it will require 1000 years, okay, for showing creep failure. This PU by 9 load, it will require 5000 years for showing creep failure. Now I am applying this load for last 500 years, and I am applying this load for last 100 years. So my cumulative damage will be nothing but 500 upon 1000 for PU by 3 plus 100 upon 5000 for PU by 9. Okay, so this is my cumulative damage. And if this value is greater than 1, then we say that total it will cause failure of concrete if this cumulative damage becomes greater than 1. If it is less than 1, then we say that creep failure has not occurred yet. Okay, so this is known as minor rules. So this again will see through an example, it will be much clearer to you. Okay, so just remember there are multiple cycles that are acting, and creep damage, the total damage, it is defined by summation of n by n. So n is the amount of time a load is applied, and capital N is the total number of uh, cycles in that load for causing creep failure. Okay. So just let's see some numericals to understand prediction and measurement of creep. Okay, so there are few numericals that are here. Okay, very simple numericals. So just think about each of these numerical, just do calculation. And in the meantime, if anyone of you has any doubt, you can ask. So first question is, I have a 500 cross 300 concrete cylinder, and it is tested as per ASTM C512 guideline under a sustained stress of 10 MPa. The elastic strain at loading was 0.0005. The measured creep strain after 1 year is 0.0012. So what is the total strain after 1 year? Can anyone tell me? This is a very simple question. So you have been given elastic strain and creep strain. So total strain will be, and what will be the creep coefficient also? If you have calculated total strain, then tell me the creep coefficient also. Okay, total strain is nothing but elastic strain plus creep strain. So it is 0.0005 plus 0.0012. So that is 0.0017. So this is total strain. And creep coefficient is nothing but creep strain upon elastic strain. So that is 0.0012 divided by 0.0005. So this is 2.4. Okay. So this is how we can read the data that is there in the numerical, and we can do calculations. So that's why the two formulas that we have discussed, the terms, the creep coefficient and the compliance factor, they are important because they will help us to quantify creep in concrete and compare different concretes. Question number 13. A concrete member is loaded at 28 days under a sustained stress of 5 MPa. So, when the concrete age was 28 days, we applied a stress of 5 MPa on the concrete. Using ACI model, estimate the creep coefficient after 180 days. Okay. So, from 28 days till 180 days, a sustained stress of 5 MPa was applied. Now we need to estimate the creep coefficient. Okay, if we know the ultimate creep coefficient was 2.35. So just think about this formula. Okay, ultimate creep is given to you. T naught, you know, it is 0.28 days. T is 180 days. Okay, so you need to determine the creep coefficient after 180 days. So I will just tell the answers because we have a lot to discuss right now. So just we need to substitute the value. So it is 2.35 times 180 minus 56, 180 minus 28 to the power zero point 0.6 whole divided by 10 plus 180 minus 28 to the power zero point 0.6. Okay, so when you will do this calculation, you will get a creep strain of 1.206. Okay, after 180 days under loading, the creep strain it will become 0.206. Okay, so if you know the creep coefficient, then based on the elastic strain in concrete that is there initially, you can calculate the creep strain also. Okay, so that is what is question number 14. Calculate the total strain if elastic strain at loading is given as 0.0008. Okay, so in this case, what will happen, since I know the creep coefficient, then what I will do, my I will calculate first the creep strain. So it will be nothing but my creep coefficient 0.206 times the elastic strain, so that is 0.0008. Okay, plus elastic strain, so that is 0.0008. So this will give me the total strain. Okay, so this is how we do the calculation here. Okay, total strain is nothing but elastic strain plus creep strain. So creep strain I can determine from this relationship between creep coefficient and creep strain and elastic strain plus elastic strain. So this value it will come out to be 0.206. Okay, upon calculation. Sorry, 1.576. So this is the total strain after 180 days. Okay, so you just need to remember these relationships that we have talked. Okay, the relationship between this relationship for estimated creep coefficient after different time, the relationship between creep strain and creep coefficient, the compliance factor if asked in exam. So in exam, any one of these numerical can come, and it will be a very simple numerical if you know the relationship. Okay, I hope everyone are clear with how we are solving these numericals. Any doubt in the numericals that we are discussing in on this slide? So you can think of question number 15 also. So there are two cyclic loadings that are applied. So 50% failure for 5,000 cycles. Okay, and there's 40% failure stress for 2,000 cycles. Okay, so using minor rules, you need to determine whether failure has occurred or not. So we have applied 5,000 cycle for this much capacity loading, and we have applied 20,000 cycles for this much capacity loading. So what minor rule says, it is summation of n by n. So it is 5,000 divided by 10,000 for first loading condition, and then it is 20,000 divided by 50,000 for second loading condition. So this will come out to be zero point 0.5 plus zero point 0.4, okay, which is equal to zero point 0.9, and this is less than 1. So we can say that according to Miner's rule, failure won't occur because creep deformation, it has not reached the failure mark. Okay, so this is how we apply Miner's rule also. So we are just adding how much creep cycles have passed by for each capacity loading. Okay, and if the summation of creep cycle they have reached one or they have exceeded one, then we say that creep deformation has occurred, failure has occurred. Okay, so these numericals are very simple. It is just the application of formula. So I request everyone just go through the numerical discussion again, all the minor rule, the measurement part, and the prediction part again, and then just solve this question by yourself. Okay, once more. Or if there is any question in the assignment also, it will be very easy for you to solve if you remember the relationships properly that are there in the ACI code and in the minor rule. Any doubt in this part? If anyone has any doubt, please feel free to ask. Okay. The more you will ask, the better it will be for the discussion also. Okay, I will quickly move to the last segment because we don't have much time left. Okay, so after creep, the final part in hardened concrete property that was discussed in week 9 was shrinkage of concrete. Okay, so we know shrinkage is nothing but volume change in concrete due to loss of moisture. Okay, we have seen the discussion on shrinkage earlier also. So there are different types of shrinkage that can be there in concrete. There's plastic shrinkage, there's drying shrinkage, there's autogeneous shrinkage, and there is carbonation shrinkage. Okay, so plastic shrinkage is contraction in volume of concrete due to water movement when concrete is in plastic state. Okay, so when concrete is in fresh state, okay, when concrete is plastic in nature, the moisture loss that is occurring from concrete, it results in plastic shrinkage. Okay, and it how why it can occur, it can occur due to water absorption by aggregate or due to moisture loss to the environment. Okay, so suppose we haven't considered the water absorption capacity of aggregate, so what will happen, aggregates will absorb some moisture from the cement paste, and that can also lead to shrinkage in concrete. Okay, that can also contribute to plastic shrinkage, or there can be moisture loss due to evaporation from the surface of concrete. So both things are there when we talk about plastic shrinkage. Then there is drying shrinkage. So since plastic shrinkage was in fresh state, the same thing is about drying shrinkage. It is from the hardened state of concrete. The shrinkage that is happening once concrete is set. And this is due to loss of adsorbed water, like the water present in gel pores or the water that is there in CSH hydrate. Okay, so the loss of water from this adsorbed water, it is known as drying shrinkage. Okay, then we have autogeneous shrinkage. Okay, so when cement and water they react, they form a cement paste. The volume of cement paste, it is smaller than the combined volume of cement plus water. Okay, so this is known as autogeneous shrinkage, or we say basic shrinkage, that is due to reaction between cement paste and water. Okay, the volume of cement paste, it is lower than the summation of individual volume of cement and water. Okay, so it does not include any direct environmental effect that such as temperature or moisture change. It is just a shrinkage which is there already inside concrete, which can't be nullified. Okay, it is due to the chemical reaction between cement and water, and its magnitude is generally very small. Okay, that's why it is normally ignored, and we don't care about autogeneous shrinkage much. And then last is carbonation shrinkage. So when CO2 it reacts with calcium hydroxide in present in concrete pores, it forms CaCO3. So this product occupies lower volume compared to CaOH whole twice. CaCO3 volume is lower compared to CaOH whole twice. So that's why there is some shrinkage here also. Again, magnitude of carbonation shrinkage is very small compared to drying shrinkage or plastic shrinkage, so it is not talked much. But it is also a type of shrinkage that one must remember. Okay, so these are the four types of shrinkage. Plastic shrinkage is in fresh state, drying shrinkage is in hardened state. Okay, then autogeneous shrinkage is due to chemical reaction between cement paste and water, and carbonation shrinkage is due to carbonation of Portland diet in hardened concrete. Now, why shrinkage occurs? Okay, so it is due to capillary action of water. Okay, so in concrete there are network of capillary pores that are present. Okay, so when concrete loses water due to evaporation, these pores they become partially empty. So suppose these are two hydration product, and the pore between them is completely filled with water. Okay, now this much amount of water has been lost due to evaporation. So what happens, these water molecule they adhere to the cement this hydration product surface through surface tension, and they form a meniscus. Okay, so this meniscus, what they do, what it does, it tries to pull the hydration products towards each other. Okay, and it generates tensile stress on hydration products, and this inward pressure that is acting on the hydration product, it causes shrinkage in concrete. Okay, so again I will explain what is happening. Concrete, it has capillary pores which is filled with water initially during mixing. Okay, during concrete mixing. Now due to drying, some of the moisture from the capillary pores that is lost, so the remaining water it forms a meniscus. Okay, it adheres to the surface of cement paste, and it forms a meniscus. Okay, and this meniscus it creates negative capillary pressure on the cement paste, and it tries to pull the cement paste towards each other. Okay, and this inward tension force that is applied on the hydration product, it leads to shrinkage deformation in concrete. Okay, so different concrete factor can affect different shrinkage. So if I increase the aggregate content, I will reduce the shrinkage. Why? Because aggregate are rigid part of concrete. They are stiffer in nature. So if I increase the aggregate content, I will reduce the cement paste content. So I will reduce the shrinkage. W by C ratio, as W by C ratio increases, the moisture inside concrete will increase. So evaporation of moisture will increase. Okay, so shrinkage will increase. Curing condition, if we cure the concrete properly, then we will have a dense microstructure. Okay, so shrinkage will reduce, while poor curing will increase the shrinkage. Relative humidity, if there is low relative humidity, then evaporation loss will be higher, so shrinkage will be higher. Volume to surface area ratio, so if I have a higher surface area of concrete, then there is more surface available for moisture loss, so shrinkage will increase. Slump, so higher slump initially means that concrete uh, is more fluid in nature. So if concrete is more fluid in nature, it is more susceptible for moisture loss, so shrinkage will increase. Then fine aggregate to total aggregate proportion. So higher fine aggregate content, it increases shrinkage. Why? Because it increases the paste volume inside concrete. Okay, so it can lead to higher shrinkage in concrete. Air content reduces shrinkage. Why? Because it provides a release of pressure. Okay, so it is like a stress relief point, like how we discussed in air and training concrete. Okay, in air and training concrete, what is happening? There is continuous expansion and contraction of water inside concrete. Okay, so when there are pores which are present inside concrete which are vacant, so this expansion and contraction, it is relieved there. Okay, so same thing is applying here also. If I have air voids inside concrete, so this tensile stress that is generated due to shrinkage, it gets relieved due to air void. Okay, however, if there is excess of air content in concrete, it will reduce the strength of concrete also, which can increase the shrinkage. So air content, though it reduces shrinkage, but if there is very high air content, it can increase the shrinkage also. And cement content, so higher cement content increases shrinkage. Why? Because there is chance for greater moisture loss from concrete because of more cement paste present in concrete. Okay, so shrinkage is primarily driven by the cement paste and not by the aggregates. Okay, so the property of cement paste, the strength of cement paste, the fluidity of cement paste, it governs the shrinkage in concrete. Then, similar to creep, shrinkage can also be determined. Okay, after time t, we have this formula for shrinkage. So, ultimate shrinkage strain, again, ACI code has a formula which calculates ultimate shrinkage strain that you have discussed in the lecture also. Okay, so this part I'm not repeating much. So, after suppose at time t naught shrinkage started, so after a time t, what will be the total shrinkage, you can determine from this formula. Okay, for different coefficient, this k1 to k7, ACI code has given tables. Okay, which can be used to calculate different factors, like how much moisture curing was done will give you the k1 factor. Then based on the volume to surface area ratio, we get the k3 factor. Then there is K2 factor based on relative humidity. Then there is K5 factor based on the uh, that is based on the fine aggregate content. Then based on cement content, we have K6 factor. Based on air void content, we have K7 factor. Based on slump, we have K4 factor. Okay, so all these factors we can calculate, and then we can estimate the ultimate shrinkage, and then that can be used to calculate shrinkage at any age. And again, similar to what we discussed in creep, there is a British standard method also which calculates shrinkage based on volume to surface area ratio and relative humidity. Okay, so knowing the relative humidity of concrete and volume to surface area ratio, so for this much amount of water initially used, there is this curve that is defined. Okay, so different water proportion shrinkage values can be calculated, corrected, but this chart is for 190 liter per meter cube of concrete. If this much water was used during concreting, so at what relative humidity, what will be my ultimate shrinkage strain, that is given in this chart. Okay, now how we measure shrinkage in lab. Okay, so on this slide there are few measurement methods for shrinkage in concrete. Okay, sample in concrete sample. So the first two image that you see here, this is known as length comparator. Okay, this is based on IS 49459 guideline. Okay, so we prepare a concrete prism. Okay, and we measure the length of this initial length of the sample we measure. Okay, by using this dial gauge, so you can see there is a reading that is coming at the top. Okay, so we place the this prism in this dial gauge, we record the length of the sample. Then after different ages, like exposure to drying condition or exposure to any other harmful condition, we expose the sample, and then we again calculate the length of the sample. Okay, so this is known as length comparator. So change in length will give me the shrinkage in the sample. So shrinkage strain is nothing but percentage change in length. Okay, original length minus final length upon original length. Okay, in this image you can see a guard ring, restrained ring test that is used to evaluate shrinkage induced cracking in concrete, and this is based on ASTM C1581 method. So okay, so in this what we do, we prepare a concrete ring around a steel ring. So this is a steel part, okay, and this is concrete around it. This is steel and this is concrete. Okay, now as a concrete undergoes shrinkage, what will happen, it will apply some strain on the steel ring. Okay, so using a strain gauge, we measure the strain that is there on the steel ring that is developed over time, and that we use to calculate the shrinkage that is occurring in concrete. Okay, and third, this image shows the setup for autogeneous shrinkage in concrete, and this is based on ASTM C6108 guideline. So in this thing you can see there is a tube, this is a cement paste at the bottom, o- okay, and this is water at the top. Okay, and there is a graduated measurement tube inserted here. Okay, so initially water will be at some mark in this tube. Now as autogeneous shrinkage will occur, the volume of this sample it will reduce. Okay, so what will happen, the amount of water in this capillary tube also it will go down. So based on the amount of decrease in volume of water in this tube, we will determine the autogeneous shrinkage that has occurred inside the cement paste. Okay, so as concrete undergoes autogeneous shrinkage, okay, the volume change that is occurring here, it will be measured by the fluid that is filled in this capillary tube. So the movement of fluid in this capillary tube will give us an indication of autogeneous shrinkage that has occurred here. And since we have inserted a rubber cork at the top and completely sealed this sample, there is no drying shrinkage or plastic shrinkage that is happening. The only shrinkage that is there here, which is possible, it is the autogeneous shrinkage only, because water is completely filled inside the tube also. So there is continuous curing that has been provided to the sample. Okay, so there is no other form of evaporation loss that is occurring here. And on this slide you can see different types of cracking pattern due to shrinkage. So you can see there is longitudinal crack due to shrinkage, there is map cracking due to shrinkage. So when you see such cracking patterns on the surface of concrete, one can predict that it is due to shrinkage. So all these cracking due to shrinkage, it comes under minor cracking category. In major cracking we have cracking due to corrosion, we have cracking due to differential settlement. Okay, all those are major cracks, while cracks due to shrinkage they come in the category of minor cracking. Okay, I hope everyone are clear with shrinkage. So the discussion for shrinkage was mostly similar to how what we discussed for creep. I guess there was some network fluctuation that happened. Can anyone tell me at which point I was when this network fluctuation happened? So just now I was discussing about how shrinkage is measured using length comparator, guard ring setup, and autogeneous shrinkage setup. And then I was talking about cracking in concrete due to shrinkage, how cracks appear and how they are classified in minor category, and what all cracks come under major category. And then I came to this slide before I switched to a presentation. Can anyone tell me where the network went off? So this at length comparator, longitudinal shrinkage, length how we measure shrinkage based on change in length, right? Is that the stage? Slide 50. Okay. So on slide 50, I was just showing you how cracking patterns appear due to shrinkage. So there will be longitudinal cracks or there will be map kind of cracking due to shrinkage. And all these cracks, they come under the category of minor cracking. Okay. Cracks due to plastic settlements or due to differential settlement or due to corrosion or due to crack due to loading of concrete, they are all major cracks. Okay, and shrinkage cracks are due to they come in the category of minor cracks. Okay, so that is what I was discussing on slide 50. Okay, so these are some questions that, since we don't have time left, so I will just ask you to try this question on your own. Okay, these are very simple question. So like, which of the following results in higher drying shrinkage? So just think about different factors and how they influence shrinkage of concrete, and you will get the answer. Okay, so just think about this question. If you are not able to if you are not able to think of the answer, you can ask me in the next slide, next meeting. Okay, similarly, question number 17, which of the following statement is false regarding shrinkage cracking? Okay, so that is again based on the factors that affect shrinkage. And question number 18 is a numerical which is very similar to how we discussed for creep. Okay, just give it a try. Okay, any doubt in the shrinkage part? This for 16 answer will be B. Why? Because higher W by C ratio, which will result in highest drying shrinkage. So at higher W by C ratio, there is more water present inside concrete. Okay, so there is more shrinkage in concrete. While higher fine aggregate proportion also increases the amount of cement paste in concrete. So again, shrinkage in concrete increases. And for question number 17, the answer is A. Which of the following statement is false? So shrinkage cracks are more likely in member with higher volume to surface area ratio. That is false. So when I talk about higher volume to surface area ratio, it means that surface area is small. If surface area is small, then moisture loss from concrete will reduce. So shrinkage cracks will reduce rather than it will increase. And question number 18. So you have shrinkage strain and you know the modulus of elasticity of concrete, so you can calculate the stress generated due to shrinkage. Okay, and if that stress due to shrinkage is more than the tensile strength of concrete, then we can say that concrete will fail. Okay, so shrinkage stress is nothing but shrinkage strain upon elastic modulus. Okay, so that will give you the shrinkage stress. Elastic modulus upon multiplied by shrinkage strain will give you the shrinkage stress, and that stress, if it is more than the tensile strength of concrete, it will cause failure of concrete. Yeah, if it is 18 MPa, 18 MPa is more than 3 MPa, it means that it will cause severe cracking in concrete. Okay, this is 18 MPa, so it is 30 into 10 to the power 9 times 600 into 10 to the power minus 6. So this will come out to be 18 MPa. And 18 MPa is more than 3 MPa. So there will be severe cracking in concrete. Okay. So such question, they have high chances that they can be asked in exams. Okay, because this is a very simple question. You are just applying three different concepts. First is how modulus of elasticity is related to stress and strain. Okay, then once you get the strain, how you are determining whether it is severe or not. Okay, so two concepts have been used here. So just go through the entire session that we have talked today and just revise it once, okay? Because these things are, they are generally new, they are not commonly taught everywhere, okay? So just go through the session again, and if anyone has any doubt, we can discuss in the next session, okay? This was all for today. So we talked about modulus of elasticity, then we talked about fatigue and bond strength, and then we talked about creep and shrinkage in concrete. What are the mechanism of creep, how we predict and measure creep and shrinkage, how different concrete factors affect creep and shrinkage, okay? And we also talk about different types of shrinkage in concrete also. Okay, thank you.